Yes? Okay. Then I went through and said that we could have used PV equals nRT. Or we could solve for n being RT over PV. Everybody remember that? We did both. Yeah, we did. It's okay. The last one I did very, very fast. So are there questions about that process, or are you okay with it? Megan, you didn't remember it. Do you want me to go through it?
No.
I don't blame you. I wouldn't want to go through it either.
This is when we were talking about the long way versus the short way?
Yep.
Okay.
So there is the long way and short way is kind of a bad way to reference it, in my opinion. There's the correct way, and then there's a shortcut that only works on every second Tuesday at midnight during a full moon.
Would it work
At winter solstice. Okay. So the short way is very, very particular. You must be at standard temperature and pressure. You must be a gas. Those conditions are, while not incredibly rare, are rare enough that it makes that conversion or that factor not very useful outside of just the context of a chemistry class. Whereas PV equals nRT will always work because you just have to put in the correct terms. PV equals nRT was our ideal gas expression, okay, which officially has its own issues because it has to be an ideal gas. Okay, and that's not the short way. PV equals nRT is the correct way. Okay, so there's correct on the bottom, and on top we have only under special conditions. Additions, I think I spelled that right. Okay. For the sake of this class and what you get tested on, unfortunately, in my opinion, unfortunately, you were tested only with the specific conditions, which then means you can use that cheat because you're only being asked questions under those special conditions. If you move into the real world, you will not be under those special conditions. You would have to use PV equals nRT. If you move into future chemistry classes, depending on your instructor, you'll go back and forth from only using special conditions or using the correct way. Okay. So I just want you to be aware of both methods, aware of the limitations within each of those. Okay. And our correct way, unfortunately, I'm missing a C, also only works if PV equals nRT is true. Well, that is only true if I'm working with an ideal gas. What if it's not an ideal gas? I think you used some choice words, but can you enunciate those words without using your choice words, Isaiah? No, you're sticking with the ones you chose. If it's not an ideal gas, this equation doesn't work, and we'd have to change our interpretation of it. And we'd end up looking at other permutations or other versions of gas laws. One of those being van der Waals gas expressions, okay, which are vastly more complicated, which is probably why we don't talk about it, because you're like, well, I don't want to make it more complicated than it already is. Fair enough. Okay. Future chemistry classes, you might see it. Make sense? I hear a word.
Yeah.
Okay, that works. So the next part, some simple or some last minute kind of things about gases before we move on. We have Dalton's law of partial pressures. Where did we hear about Dalton before? Beginning of the semester, we came up with kind of our basic fundamental principles on how we put molecules together or take atoms and make molecules. Okay, most of his theorems were wrong, but they were pretty solid for as old as they were. Okay, he was also able to contribute to our understanding of gas laws. And what he went through and noticed was that if we look at the individual pressures of all of the different particles that are present, and we add all of their individual pressures up, that will equal then the total pressure within the system, okay, which is kind of a duh statement when you say it out loud. You take the pressure of every single particle, its force it's exerting on the environment, and you add all of those pressures up, well, yeah, that should be the total pressure. But that's what Dalton's law is saying. So the question then becomes is how do we use it? So if we take a sample of noble gases, any ideas why I would pick noble gases and not, say, other gases? So they are, I do know they're gases, but the larger issue, the noble gases, by definition, don't react with each other. Which means by looking at the noble gases, I'm looking at, back to our previous statement, PV equals nRT is only valid when? No, PV equals ideal gas. In our ideal gas assumptions, do our gas particles interact with each other? No. Why are we looking at noble gases? Because noble gases don't react with each other. Okay? So we're picking noble gases when we're looking at this because we know those don't interact with each other. Okay? So that allows our ideal gas law to hold true. The rest of Dalton's assumptions are going to hold true as well. Okay? So that's why I picked those. So we've got helium, neon, argon, and krypton. Well, that was a lot of them. Okay? If the partial pressure of helium is 125 millimeters mercury, okay, neon is 45 millimeters mercury, argon 158, krypton 17. What is the total pressure of the sample? Okay, well, without Dalton's law, how would we figure out total pressure? But that's Dalton's law. Okay, without Dalton's law, we'd go into the experiment, we'd add them all into a container at those pressures, and we'd see what the total pressure was. We'd find out that, yes, it was adding all of them. That's why we get Dalton's law. Okay, so you just experimentally put all these things together and notice, oh, it's the sum of all the pressures. So our total pressure is going to be what? You should be able to walk me through this calculation pretty easily, hopefully.
125 milliliters of Hg's magnesium, right?
Hg is not magnesium, it's mercury. 125 millimeters of mercury.
45 milliliters.
Plus 45 millimeters, whoops,
Plus 158 millimeters. Plus
thoroughly exciting. Can we do addition? Yeah, there we go. We have our answer. All we do is add it all up. What's our issue?
Mercury is a liquid, and in order for it to be a gas, it has to be the same temperature.
This millimeters of mercury, is it referencing mercury? No, it's a unit that represents the pressure of the gas. Okay. So we are looking at 17 millimeters mercury is a way to monitor the pressure that krypton is exerting on the environment. It is not mercury that I'm looking at. Okay. So this would go back to what are the units of pressure. Remember that slide that had like 4 or 5 different units of pressure? Yes, it sucks. Okay. What if I had instead written this? Well, that would change this one to be ATMs. Would it now just be a simple sum of all of those?
No.
Why not?
We have to convert them all to the same.
The units aren't all the same. I have to make sure the units are all the same before I could add them all up. Okay? So that would be a particularly irritating question, which is why I didn't ask it, because I didn't want to do that unit conversion. So let's take it back to millimeters mercury. Okay, Emily, I think I saw you pulling out a calculator. Did you calculate it?
Yeah, it's 345 millimeters.
Just because we've been good at this. Is that the correct answer? How many people think it's the correct answer? How many people think it's not the correct answer? Ooh, okay. I rose my hand both times just to mess with you. Okay, why do you think it's not the correct answer? 1, 2, 3. 1, 2. 1, 2, 3. 1, 2. So now I'm hearing 340. Would 340 be a correct answer? No. Okay, 350. So you're saying a rounding. So a sig figs issue pops up. Go ahead, Alexander. Walk me through it. What are you thinking? What's bothering you? But each of those are a measured value that are only accurate to that place, okay, to that number of sig figs. So I'm now hearing that potentially we should have 350 millimeters mercury because we only have 2 sig figs in our numbers. Our fewest number of sig figs is 2 sig figs, which then means our answer needs to go to 2 sig figs. Is that what I'm hearing is a valid answer? So I could go through and say 35 times 10s. I could convert it to powers of 10. By writing 350, that is 2 sig figs. The 0 now doesn't count as a significant digit because there's no decimal point. The instant I put in a decimal point, the 0 becomes significant. So if I get rid of that decimal point, it's only 2 sig figs. That goes back to our sig fig rules. You should go back and review those. Jocelyn, I think I saw you questioning something else.
I was just trying to remember like the additions, like the multiplication and the addition is different when it comes to sig figures.
Interesting. When we multiply numbers, what's our sig fig rule? It's the fewest sig figs. In addition, subtraction, it's the least precise place. Where's the least precise place? The ones place, which means my answer needs to be reported to the ones place, which means my answer is 345 is the answer. Why do we have more sig figs? When we add numbers, we have the possibility of increasing the number of sig figs. This is why we have to be careful with our rules when we go through and do our multiplication, division, addition, subtraction, that we look back at those sig fig rules. If you don't remember them, you must review them. Okay? Yes?
Can you explain that one more time because the way you explained why that's okay does not make sense.
Okay. So it goes back to, and unfortunately, it's not in this slideshow. I can't even go all the way back to it. Okay, actually, here, let's just do this. Let's just open up the other slideshow where we can look at the rules. Probably shouldn't whistle next to the microphone, which I know you can't see right now, but our pressure came out of that calculation as 345 millimeters mercury. To determine the sig figs, we'd have to do what was our mathematical operation. Okay, as it's written, I see 3 sig figs. Okay. How many of those am I allowed to keep according to our significant figure rules? That comes back to the calculation we did. The calculation was addition, subtraction, the least precise place. So I need all those numbers. The least precise place, what is the least precise place in 125 millimeters mercury? The 5, the ones place. In neon, it is 45 millimeters mercury for neon. The 5, which is the ones place. Argon, 158 millimeters mercury. The ones place. Krypton, again, the ones place. This means when I do the calculation, it is fine to punch into the calculator and have the calculator spit out whatever number you get. But you then must analyze that number according to sig fig rules and ensure that you are reporting to the ones place, which in this case means we end up with more sig figs than we started with, which is allowed to happen in addition. What if we'd done subtraction?
We would have done what we did.
Close. If we did subtraction, we run into the possibility of losing sig figs. Okay, because you're subtracting. Okay. Everyone good with that now? So we did a little bit of gas law stuff and then some sig fig stuff. Okay. Absolute zero, just kind of an interesting observation, which really comes out of our ideal gas law. Okay, if we look at a plot of volume and temperature, if I drop the temperature or even pressure, if I drop the temperature all the way down to 0, so PV equals nRT. What happens if my temperature becomes 0? So if I have gas, there's some amount of moles. Let's say I have 1 mole. Well, R is always the same. It's a constant. What does that mean about P and B, or P or V? At least one of them must be 0. Okay? That is our absolute 0 value for our temperature. If we drop all the way to that value, pressure and volume must be 0. What happens if I go negative? Could I go to a negative temperature? What would that then mean pressure or volume have to be? Negative. Can I have a negative pressure?
Yes. Well, no.
No. The pressure is the force being exerted outwards. Can I have a force being exerted inwards by a gas particle? If there's something there, it's pushing outwards. To get a negative pressure, that something is drawing things inwards. Which doesn't make physical sense. Okay. And an implosion, it's not the inside pulling in, it's the outside pushing in. Okay. It's the force from your external environment.
So then what, like a black hole, would that have like a negative?
So we could potentially see something like a black hole, okay, as a possibility. Okay. It's really just coming down to what's happening at that point. At absolute 0, nothing exists. Okay? It's kind of a weird statement. Nothing exists. How does that happen?
You just said it at absolute 0.
So one of the things that's tricky is that makes absolute 0 very difficult to obtain. Because if we get to absolute 0, then
We have no evidence of ever happening.
nothing's there. How would we observe that we were there if nothing was there?
Yeah, wouldn't that cause like a weird thing?
Yeah, we get weird paradoxes within that.
Yeah,
Yes.
Like, whatever material you did to make that happen would go with you.
Yep.
Everything in the room would go with it.
And this is why we end up with the Kelvin scale. It gives us an absolute 0. Everything we monitor after that will be positive. We can't go negative. This makes things easier for our calculations because I don't have to incorporate a negative sign and then have that mess with things. Okay? So this is one of the reasons we invented Kelvin as a temperature scale. We know it will always be positive. That said, leave it to a physicist to mess with everything. They've actually determined or come up with theoretical ways to generate negative temperatures, negative kelvins. Thank you, physicists, for making life miserable. Okay. But for the sake of our class, absolute 0, we can't go lower than that. We can't achieve 0 either. We'll always be positive. So that 273 that we end up adding in comes from extrapolating this backwards. Okay. How does that Kelvin value convert to our degrees Celsius? Okay. Kind of neat. That's just what it is. So now we run into our next concept, okay, which is can be a bit of a doozy. So we're now going back away from liquids and back away from gases, back to the equation concept and what we can do with an equation. Okay? So to ease our way into that, let's pick a really simple equation. Let's look at how we build a cheese sandwich. And please don't challenge my cheese sandwich. Well, what's your question? This is very similar to the bike thing. But everybody seems to get sick of the bike thing, so we will switch to cheese sandwiches. Right? So let's take a look at a cheese sandwich. How do we make a cheese sandwich? Okay. Yeah, I would argue that it's really just a bread sandwich. But okay. We need cheese. We need bread. Okay. We're going to make a whole sandwich. We'll need 2 slices of bread. Put the cheese in it. We now have cheese sandwich. And we can grill it up, and we got a cheese sandwich. So that's our basic formula or our basic equation for making a cheese sandwich. And you can argue this may be a crappy sandwich, and I would agree with you, but this is our basic formula to make that sandwich. Everybody okay with that formula? What do you mean it's not balanced?
Because you don't have the evidence cheese and bread on the other side. Need more cheese.
So you may not like...
If you were to make a cheese bread as a unit instead of
Oh, okay. So let's switch our sandwich name and make that instead what?
cheesy bread. Grilled cheese sandwich. Bread sandwich.
Oh, hey.
How about that?
Okay, 2 slices of bread, 1 cheese. There we go. There's my formula for a sandwich.
It's not something different, it's just two things.
Okay. So really all we're trying to do is the same thing we're doing in chemistry. We're coming up with a notation that allows us to better see those relationships. Okay? Sometimes those relationships are obvious in our nomenclature, sometimes they're not. Okay? So in this case, we've made it a little bit more obvious on how our sandwich is made. But we have questions on that. Everybody good with it now? Okay. If you have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make? No double deckers. That's not our formula. We have to stick to our formula. How many sandwiches can we make? I'm hearing 4 and 5. Oh, that's interesting. How did you come up with 5? What did you look at to come up with 5?
I look at 5 slices of bread with bread.
5 slices of cheese. So really what you've internalized is our 5 cheese, which I'm going to abbreviate as our C. And I'm trying to convert that into my sandwiches, right? And what is the conversion factor between sandwiches and cheese? 1 sandwich is 1 cheese, which then means I end up with 5 sandwiches. So I agree. You get 5 sandwiches. Why did everybody else get only 4 and not 5? Because that says there's 5.
Because the conversion of bread to sandwich is
What we also have to go through and do is take a look at our bread. We have 8 slices of bread. I'm trying to convert my bread into a sandwich. What's the conversion factor there? 1 sandwich is 2 pieces of bread. This gets me 4 sandwiches. Now that I'm in the same unit, I can now compare those. Which of those is now going to produce the most amount of sandwiches that I can possibly make? What's that? So what's the most possible number of sandwiches that I can make? I can only make 4, which is weird because I said most possible. Isn't 4 smaller than 5? When we're looking at our limiting reactant, we're going to be looking at the smallest value. That's going to determine our maximal amount, which is a really weird statement, but that's what's happening. Does that make sense? Okay. So in running this, we end up with an extra slice of cheese. We could add another slice of cheese to another sandwich, make it extra cheesy, or you could just eat the cheese. Okay. We don't have any crackers. Okay. I would argue the biggest thing we're missing is mustard. You need mustard on the sandwich. You need mustard. Not that yellow French's stuff. You need like a good, oh, yeah, absolutely. Absolutely. You need like a little, not a Dijon, a stone ground. Yeah. So, that is our limiting reactant concept. Okay. What was our limiting reactant? What limited the number of sandwiches I could make? The bread. So bread is my limiting reactant. What would that make my cheese? The excess reagent. The thing I have extra. That's it. That's all we're really trying to do.
Oh, so I guess if you think about it, you have a bunch of reactants, whatever doesn't react with it
Is left over. Yeah, just a leftover piece. It doesn't disappear. It's still there. It's just left over. Okay? So what if we have enough bread for 4 sandwiches? Never mind. I said that. So there we go. We got all our answers. What are you guys doing? Okay. Okay, so we're just going to accept that and move on. So what's going to happen now? Now we look at this question or this equation, and now everybody's going to get it wrong. Okay? And that's exactly what I'm going to suspect is going to happen, but I'm going to let you try and go through and do it. So we've got an equation, same thing that we had before. We have an equation now to make sodium hydrogen carbonate, whereas before we had the equation to make cheese sandwiches. Okay? If I take 2 moles of sodium hydrogen or sodium carbonate and I mix that with 2 moles of water and 1 mole of carbon dioxide, then how many moles of sodium hydrogen carbonate can be produced in this? Okay. Remember with the last question, how many reagents did we have? 2. And when we did that question to solve all the way out, how many equations or solves did we end up coming up with? 2. We need to solve for the amount of sandwiches that could be made for each of those reagents independent of the other one. How many reagents do we have now? 3, which means how many solves do we need? 3. Okay. Should we actually divide this up across the class? You guys think you can work through it all on your own? You got it. Okay. Have you got... What we want? What do we want? Starting with what?
Starting with 2 sodium carbonate.
I do not accept 2 sodium carbonates.
2 moles.
Thank you. Moles of our sodium carbonate. Is sodium carbonate the same thing as sodium hydrogen carbonate?
Yep.
So what do I need to do?
Conversion.
I need to do a conversion factor. Okay, I can't just add hydrogen to it. I have to run through the reaction shown. Hydrogen is not a reagent. I can't just throw hydrogen onto it. I have to do a conversion through that reaction. The moles of sodium carbonate needs to show up on the bottom because
What you're trying to get rid of.
I'm trying to get rid of that unit. And ideally I make it into what I'm trying to get to, which is moles of our sodium hydrogen carbonate. What are the numbers associated with those units? 2 moles what? Of our sodium hydrogen carbonate, and we get that 2 from the balanced equation. Okay? What number shows up in front of moles of sodium carbonate? 1, because balanced equation. Okay? I look at the number in front of sodium carbonate in our balanced equation, and it's 1. This gives me an answer. If I can do that calculation, so 2 divided by 1, carry the 3, divided by 6. 2 times 2 gets me. That was funny. Thank you, Tanner, for at least smiling. Everybody else can.
I was so confused.
No.
You're like, how are you dividing by 3? No. 4 moles of sodium hydrogen carbonate. If I make what assumption? That the limiting reactant is sodium carbonate. Okay? Is that a valid assumption? I don't know. I have to test it. So what do I have to do?
Test your water now.
I will now go through and test the water doing the same thing. 2 moles of water. And I need to convert this now into moles of sodium hydrogen carbonate. To do that, I need a conversion factor. That conversion factor, moles of H2O, needs to be on the bottom so that... Feel free to finish that sentence anytime. The moles of water cancel out. What do I want to see on top? The moles of sodium hydrogen carbonate. What numbers are associated with that conversion factor? 2 moles of sodium hydrogen carbonate, because the 2 comes from the coefficient in the balanced equation. And the 1 comes from the coefficient in the balanced equation. Okay? Which then gets me 4. Okay? What assumption did I make to get that answer? That water was the limiting reactant. Well, this is interesting. Both those equations get me 4 moles. So I could just say, well, isn't that the answer? Those people that went through and solved it all the way would be, no, we have to do one more test. What is that one more test? 1 mole of carbon dioxide needs to get converted into moles of our sodium hydrogen carbonate. Again, my conversion factor, 2 moles. Sodium hydrogen carbonate was 1 mole of CO2. Those numbers came from the balanced equation. 1 times 2 gets me 2. Now the most sodium hydrogen carbonate I can make ends up being 2, because I have now run out of carbon dioxide and I cannot make any more. So the reaction stops there. The limiting reagent ends up being my CO2. Make sense?
Limiting reactant as well.
Sorry, limiting reagent, limiting reactant, same thing. Okay. Could we make this more complex?
Yes.
Absolutely. Instead of giving you moles, I could have given you,
Chicken Skittle words.
yeah, theoretically we could have done all that. But let's pick a more reasonable, grams. Okay. Can we use grams from our balanced equation? No. Our balanced equation does not include mass. The balanced equation only tells you the number of particles there. So what do we have to do as a first step? Convert the grams to moles. Then once I'm in moles, now I can use the balanced equation. I can convert the moles into moles of the next thing. And I can now do my comparison.
That's like an extra step that was used.
Okay. And instead of doing grams, I could have done pressure. Okay. Using our gases. Okay. We could have potentially used volume. Volume gets a little bit dicey. Okay. We could have used volume. Oh yeah, sorry. Volume and molarity as our conversion factor if we were using a solution. Okay. So we can layer in a whole bunch of extra calculations into it. Ultimately, it's still going back to the same thing. We're using the balanced equation to look at the relationship between our reactants and our products and how that allows us to interpret what we can get out of our equation or out of an individual reaction. Does that make sense? Adam?
Am I working ahead if I ask how to find out how much CO2 we're missing? Like, because I know, isn't there a way to figure out?
So there's an interesting question. What else could we ask here? What if I want to get 4 moles of sodium hydrogen carbonate? Okay. I'm missing CO2. So a question could be, how much more CO2 do I have to add to get 4 moles of sodium hydrogen carbonate? Yes, I could ask that question. Okay. I could also ask, how much sodium carbonate is in excess? How much extra do I have left over? So if we thought back to our sandwiches, how much cheese did we have left over? We just had 1 slice of cheese. We can do that same type of question back with our chemistry reactions. Okay. Now the question should be, am I going to do that to you? No. Okay. If you move into 151, you should fully expect that level of calculation. Though based on what I'm seeing in organic about limiting reagents, it looks like they aren't asking those level of questions. Okay, but theoretically, you're able to do that. Okay, does that make sense?
So all we'll have to do is just find what the limiting reactant is.
That's it. Okay. So the next concept on top of this. Okay, we ran through this reaction. We said the limiting reagent was our CO2, right? We had 1 mole of CO2. And that led to how many moles? I already forgot. 2 moles? 2 moles of our sodium hydrogen carbonate. Okay. We now go into the lab and test this for real. Because right here we're just saying this is what should happen. I now go into the lab and actually do it. I tell you to do it. You run through all your calculations, and at the end of that, you find out that you produce 1.9 moles of sodium hydrogen carbonate. Okay. Dang it, why is that a problem? Okay. Will our reactions ever go perfectly?
No.
Never. Okay. In fact, that is a common grading method by most instructors. We look at your result. Did you get a perfect result? You cheated. Okay. Really kind of straightforward and blatant. I think a few people encountered that. I think that was with you guys, didn't I? Kind of yell at you guys that you came out with the exact mass? I don't remember. Okay. That if you end up getting the exact result that you were supposed to have gotten, you did something wrong. Okay. This is because science does not work perfectly. Something always fails. Okay. Something will always go wrong, causing your result to skew or shift. Okay? So we want to come up with some way to present potentially our result. Okay, so let's ignore the amounts given. Okay, let's say we both ran this reaction. We don't know how much we started with of anything, but you guys run through this reaction and you obtain 2 moles of sodium hydrogen carbonate. Okay. I go through and do it and I obtain 20 moles. Who did it better? Okay, neither I kind of accept. What do you mean by neither? Can you elaborate on that? You produced 2, I produced 20. Who did it better?
It depends how much you are.
Excuse me, what?
It depends how much you are at first.
Okay. Theoretically, you were supposed to produce 4 moles. Theoretically, I was supposed to produce 50 billion moles. Who did it better? You guys did it better. You were supposed to produce 4, you produced 2. It's about half right. I was supposed to produce 50 billion, and I instead produced 20. That's a little bit worse than half right. Okay. So when we're looking at our results, we don't want to say, this is how much was produced and now I'm great. Okay. What we need to evaluate is come up with some way to normalize that data. Okay. If you get a 90 on the next exam, is that good or bad?
Good.
The next exam is worth 1,000 points.
Are you serious?
90 is not really good now. Okay? It's all dependent on what you could have possibly gotten. So when we think 90, you're referencing a 90%. Okay, a 90%, yes, is good. But how did we calculate the percent? We looked at what we got and we compared that to what we could have got. An actual result versus a theoretical result. That comparison is our percent yield. For those of you panicking that the next exam is worth 1,000 points, it's not. No. Okay, don't worry about that. Just an example. So to calculate a percent yield, we will take our actual yield, or what we've experimentally determined, and we will divide that by our theoretical yield. How do we determine the theoretical yield? That's going to be dependent on the limiting reagent. So to determine the theoretical yield, we must do a limiting reagent calculation. So officially, to run a percent yield question, you'll take an actual value that you're given, and then you'll have to do a limiting reagent calculation to determine the theoretical yield. Okay? You can then punch it into your calculator and get your result.
So it's like, you want to make 5 sandwiches, but you can't, because you
Yes,
end up 100, but you only make
exactly right. Or if you were trying, if we go back to the sandwich one, as you're trying to make sandwiches, you were supposed to make 4, but you only made 3. What happened? Your roommate came in and stole some bread and cheese.
yeah, so it's
Okay? Your yield has now gone down.
by 1/4, right? So it's
If you wanted to really get specifics, yeah, something like that. What are our units on our percent yield? This is a trickier question.
Wouldn't the units just be the units you wanted from the previous question?
Close.
your theoretical value.
The units, there are none. The units on your actual yield must be the same as the units on
The theoretical
theoretical yield, which means when you do the division,
is 2% of that yield.
the units cancel out. Okay?
So it's just a number.
So it's just a number. So you will have no units associated with your percent yield. Okay? You have to make sure those units are the same. Okay? So, here's a new question. And if you did all the work, then maybe this would have helped. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. And here's our extra piece of information. We were only able to produce 0.5 or only 0.5 moles of sodium hydrogen carbonate are produced. What is the percent yield for the sodium hydrogen carbonate?
25,000. Is it balanced?
Okay? We have to go through and do all of our calculations. Remember, to get the percent yield, how do we calculate it? Percent yield was our actual over our theoretical, but the theoretical is a new term. What did we say the theoretical needed to be? The limiting reagent. Okay, it's our limiting reagent theoretical. Actually, here, let's do it this way. It is our theoretical that we determine from the limiting reagent. Does that make sense? Okay. And then we have to multiply by 100%. Okay. What was the actual yield? 0.5 what? Moles of sodium hydrogen carbonate. We need to then divide that by our moles of sodium hydrogen carbonate, and the number that we need to bring in there has to come from our theoretical yield calculation. Okay. Did we do a theoretical yield calculation already for this question? Yes. And in that we found the limiting reagent was our carbon dioxide as our limiting reagent, which then resulted in 2 moles of our sodium hydrogen carbonate. We can sub the 2 in. We get 0.5 divided by 2, and our answer becomes
1. No.
what was that? 25% yield. Okay? Questions about that? So for those of us that were really good in our head, yes, you did a good job calculating that in your head. So good job. Okay? Yes?
25%.
That means when we ran this experiment, we obtained 25% of the maximal value we could have for our sodium hydrogen carbonate. Okay? So this, I could have obtained 2 moles. Well, I only ended up with 0.5. 0.5 was 25% of 2. Kind of make sense? Okay. Yes, yeah.
Can you explain why you put 2 moles of sodium hydrogen carbonate on the bottom when carbon dioxide was our limiting reactant?
So carbon dioxide is our limiting reactant, but remember the number that we inserted here, the units must be the same. Okay? So since I have defined my actual yield as moles of sodium hydrogen carbonate, what unit must show up on the bottom? Moles of sodium hydrogen carbonate. The number that I put in there has to come from my limiting reactant, which was CO2. Okay, so that's what we did when we looked at the limiting reactant side. We had 1 mole, of CO2. This needed to be converted to moles of sodium hydrogen carbonate, right? Our conversion factor. 2 moles sodium hydrogen carbonate, 1 mole CO2. 1 times 2. What's that?
So whatever we produced for the limiting reactant was our number for the theoretical on the bottom.
Yes. After running that calculation, yes. Okay. Other questions?
Is the unit for that just percent yield?
Yep. It's just our percent yield.
So, I'm just trying to figure out. So the question asked you what is the percent yield of such and such, but then the question would be, so trying to figure out you got 0.5 sodium hydrogen carbonate, and then you go to that.
Where did I get 0.5 moles of sodium hydrogen carbonate? It was given to you in the question. You will always be given the actual yield. You can never calculate the actual yield because it's what you actually obtained. You have to be given that number. Okay, that's what happens in the lab. Okay. Limiting reactant and percent yield. So here's a fun little question. A 50.6 gram sample of magnesium hydroxide is reacted with a 45.0 gram sample of hydrochloric acid. At the end of the reaction, a chemist recorded a dry mass of 60.0 grams of magnesium chloride. What was the percent yield? said was your first step, which I'm still noticing people, even when I tell you what your step is, you're being like, well, I don't want to do it. Okay? It's fine. You'll get it wrong. But that's fine. You can do that. That is your right. Our first step is to come up with the balanced equation. We need an equation. So we write down our reactants. We have to do our nomenclature to predict what those reactants are. Notice magnesium hydroxide is MgOH2. Why do I need 2 hydroxides? Magnesium is a +2. I have to use that nomenclature system. Hydrochloric acid, I know, is HCl. I know I don't have any other numbers associated with that because hydrogen and chloride are both 1 but opposite charges. Okay? What type of reaction would I be running here? Okay. 2 answers that work. Neutralization is a big tip-off because I see H and I see OH. And if we think back to what I wrote out on the slides for neutralization, oh, it had H and OH. That's why you need to memorize those patterns, because with that information, what can I now do? Predict the products. If I don't know what type of reaction is happening, I cannot predict the products. You're done before you even start. Okay? The other answer is a double replacement. Both of those would work. So we exchange out. I would get the magnesium with the chloride, and I would get hydrogen with the OH. Before I continue, I must make sure those formulas are correct. The charge on magnesium is +2. The charge on chloride is -1. Is my formula correct? What do I do to fix it? I need 2 chlorides. So I get MgCl2. We go through and take a look at our HOH. Hydrogen is a +1. Hydroxide is -1. Is that formula correct? Yes. Now that I've predicted my products, I can now go through and balance the equation. Is the equation balanced? No. Quickly, what we would need, 2 HCl, and officially 2 water. Did I do that right? Yeah. Okay. You should be balancing that quickly. Ideally, you're showing your work to set that up. Okay. We now have a balanced equation. Okay. We could go through and say, well, what are we really trying to get through? Do I even need that? For a percent yield, it is the actual over the theoretical, where the units must be the same. The actual is given to me. It must always be given to me, unless I'm solving directly for that, which changes the calculations around a little bit. Am I given the actual yield? What is it? 60 grams is wrong. 60 grams of magnesium, already forgot, sorry, chloride. I need to divide that by what? Grams of magnesium chloride from my limiting reagent. That is a calculation. I must calculate that. Okay? That means I now have to go back up and say, okay, well, what did I start with? Okay? Well, I have the possibility, we can write these things underneath, 50.6 grams of magnesium hydroxide. What was the other one? 45? 0 grams of our hydrochloric acid. I have to now convert those into magnesium chloride. So to do that, I'm trying to get what unit? Really? Moles? What's it say at the bottom? Grams of magnesium chloride. That's what I'm trying to get to. So let's try and get there as quickly as possible. What am I starting with? Well, I will assume that magnesium hydroxide is my limiting reagent, which means I'm starting with 50.6 grams of magnesium hydroxide. I definitely did not give myself enough space, so we'll have to cram it in here. Is grams of magnesium hydroxide the same thing as magnesium chloride? No. So I need to do a conversion factor. Okay. I need to convert substances. How do I convert substances? We will need grams to moles, yes. But how do I convert the substance? So grams to moles is converting the unit. I want the substance. There's only one place to get the substance conversion, the balanced equation. And the units in the balanced equation are moles, which means the very first thing I need to do, get those grams of magnesium hydroxide converted into moles of magnesium hydroxide. Where do I find that conversion factor? the periodic table. And I do that by adding up the molar mass of every element on the periodic table in that formula. So I add up the mass of magnesium plus the mass of oxygen times 2, because that's what the formula is. There's 2 oxygens in magnesium hydroxide, plus the mass of 2 hydrogens. Anybody get that number? 58.
If you average the magnesium down to 24.
I'm fine with that. Okay. We're now in moles of magnesium hydroxide. What do I want? I want a different substance, so I'm going to have to convert the moles of magnesium hydroxide into magnesium chloride. Why do I put the magnesium hydroxide on the bottom? So the units cancel. Where do I find that conversion factor? The balanced equation. Okay. What is the coefficient for magnesium chloride? Coefficient for magnesium hydroxide? 1. I'm now in moles of magnesium chloride. What did I say I wanted for our final answer? Grams of magnesium chloride. What do I need to do? I need to get rid of the moles of magnesium chloride, and I need grams of magnesium chloride. Where do I find that value? Periodic table. Did anybody get that one? Did you? What'd you get? Sorry? 95 ballpark grams of magnesium chloride over 1 mole of magnesium chloride. I now have my final answer for units, grams of magnesium chloride. I can punch it in the calculator. Did you actually get a number for this, Obed? Nate did. What'd you get, Nate? 82 point what? 53 grams of magnesium chloride. Should I now take that number and put it in down here?
No.
Why not? I'm also going to have to test out the hydrochloric acid. So the calculation I just did, I now repeat, starting with the hydrochloric acid to see what number I get. Then what do? Add them? No. The smallest of those 2 numbers can now be plugged in for my solve, and I can get the final answer. We will pick up with that on Thursday. God, it's only Tuesday. We'll pick up with that on Thursday. With the second half of that, we'll get an answer, and we'll discuss that answer on Thursday, and then we'll finish off the rest of the slides, which is empirical and molecular formulas, hopefully with enough time for review. That review is going to be driven by your questions.